Yeah.
Okay. Thank you, everyone, for coming to another one of our seminars. And today we have a guest speaker who's been with us here at the university for the last 6 months. And Professor Tumler said you're leaving here relatively soon. But he's going to talk about some of his research on freezing and thawing behavior of soils. He's a visiting scholar here from Beijing, Jiatong University, and his name is Jiankun Liu. And he's got a degree from Lenzhou University in China and a PhD from Moscow State University in civil engineering, 1994. And we're looking forward to hearing about some important research here. We have freeze-thaw behavior, so we hopefully can learn something here about what's going on with freeze-thaw and railway practices. So let's welcome Professor Liu.
Thank you. Thank you, Jeffrey, for the introduction. Hello, everybody. At first, I'd like to give my special thanks to Professor Tumler. He's kindly invited me for 6 months visit. I really enjoy my work and stay here, both in work and life. My presentation will finish in about 40 minutes, so I won't take much of your time. Some of them may be very basic stuff. So if you have already had this knowledge, please just ignore it. Mostly for freezing soil, we have several aspects. Frost heave, permafrost, soil weakening, and freezing soil effect. And later, I will give some measures for the Xinhai Tibet Railway subgrade. Probably you know or not, nearly 50% of the world land located subject to the freezing soil effect. And among them, 25% is permafrost. This is mainly in Alaska, Canada, and Russia, and in China, in Tibet. In Tibet, it is because of very high altitude. The soil freezing, the temperature lowering from the top to the knees, the water in soil will become to froze. You will have a freezing front here, moving from upside down, and the moisture will migrate to the front. So in this case, the soil will become freeze, and the frost head will have. This is bad for our civil engineering. Suppose you have a pile considered in summer, and in winter, probably you will jack out, and in the spring again, it will become unstable. And this really happened in reality. This is the pipeline, the foundation for the water pipe in Russia. This is the original height. You can see how much jack out. And this is the temperature monitoring platform we monitored in 2004. This is the first year, and the second year. And I'm sorry, this is the second year, the fourth year. So you can see how much jack out. When the soil freezing, very big negative pressure occurred. Probably you know many people are studying the unsaturated soil. In unsaturated soil, traditionally we have that much negative pressure. And for soil, when temperature go below the 0, they will get that much. So for unsaturated soil, I think it's easier. For our frozen soil is much, much difficult. How to predict the frost heave? Suppose you have a soil with porosity of 40%. All this water become ice. It has only 3.4%. But in reality, you observe much more frost heave. This is because this kind of water migrated from beneath to the front should be taken into consideration. This kind of problem not only interested for civil engineer, but also interested to the mathematicians. Because suppose you have a physical domain, you have frozen soil front moving from one side to the other side. This side is frozen, that side is unfrozen. the physical and mechanical property will be quite different from one from another, and you have a moving front. This kind of problem is very interesting for mathematicians. You have several processes: thermal transfer and heat transfer and moisture migration, and this temperature and moisture change will lead to the change in stress state. So it's a very complete process. It's actually a couple of processes. Usually, traditionally, we had two theories to predict the freezing thawing process. The first one, the traditional one, is is called primary capillary theory. Actually, in this theory, a very sharp interface between the frozen and unfrozen regions exists. The water flow in frozen part was also regarded to obey the Darcy's law, so it is easy to use the traditional equations. All these professors use this theory to predict the first half. They just give a criteria how much water become ice. And the second first half theory is to predict the real occurred layered ice. In reality, you will usually find one layer ice, one layer soil, and one layer ice. That's the reality. So in this model, it is assumed that the particles are held stationary, and the newly formed ice in frozen fringe moves towards the ice, towards the lower temperature. And the first half is defined by the ice velocity. This is also called a rigid ice model. And in the 1980s, Professor Conrad from Canada, they proposed the concept of ice segregation potential. The potential is the velocity of migration of water over the temperature gradient. Having this potential can be measured in a laboratory for different soils. So having this potential, you can define this velocity. So this kind of migrated water can be compulated for one dimensional case. In nowadays, many models to predict the frost half. No one give a very perfect results. The most successful is the laboratory one for one-dimensional solution. But in reality, what we need is a differential frost half. It's very difficult to predict. The permafrost. For the soils permanently in frozen state, usually we study the deformation, the strains. This is Professor Sidovici is a professor from Moscow Civil Engineering University. He began actually, this is the foundation. He began the soil mechanics, frozen soil mechanics, and rheology, long-term strains, because all the deformation and strains will depend on time, depend on temperature. So this is the two very specific features: temperature dependent and time dependent. Suppose you have a sand. For sand, usually we have the strains envelope like this, right? But when in frozen state, it will become larger. The friction angle will look like this envelope. It's much higher. But when the pressure is high, confining pressure is higher, gradually transition to the original one. This is because in higher temperature, confining pressure, the ice will thaw. Professor Vela from Moscow Civil Engineering University also wrote a book. Actually, he began in 1950s, the rheology of the frozen soil. And in 2004, he published a new book when he was nearly cannot see anything. He just dictated all his theory in memory. His assistants write down all this book, and we and my students translate into Chinese. This is the typical strain rate and relationship. For sowing soil, when the soil in frozen state become to soil, you can find a sudden change in volume. Here, this side is in frozen state, this side is in solid state. This is because there is a difference in density in water and ice. The water is one, the ice is less, is lighter. And there is also a difference in conductivity. For the ice, the conductivity is like this, and in positive temperature, there is a sudden change here. What we can see is the settlement in civil engineering. The settlement, the most successful is the formula equation proposed by Professor Sitovich from Moscow. It's widely used. This is the traditional part. This is the for sowing part. There is some professors, they give analytical solution for the one-dimensional soil consolidation process. When the soil is sowing from one side, and there will be a moving interface, sowing and frozen. And Professor Zalewski from Moscow gave a very perfect one-dimensional solution. This is effective stress. This is the position of the sowing depth. This is the pore water pressure. And he gave a solution for one-dimensional one. But in reality, what we need is the differential soil settlement. He gave a formulation. This is the three-dimensional one, but until now, nobody can give a three-dimensional solution for this soil consolidation problems. And the soil, the property of soil may be changed after many freezing sowing cycles. In some places, for example, in Tibet, you already have a very big difference in temperature between daytime and nighttime. Daytime and nighttime will be, in the daytime maybe positive, and in nighttime will be maybe negative pressure. So many freezing sowing cycles will subject to soil. Most people reported that, some people reported that for after freezing sowing cycles become looser. And some people reported after freezing sowing cycle, soil density become denser. And in 1999, Professor Wacklander from Sweden, he summarized all these data. He came to the conclusion that for loose soil after freezing sowing cycles, they will become dense. For dense soil after freezing sowing cycle, will become loose. And later, this also his results also support this kind of opinion. Originally, loose will become dense. Originally, dense will become loose for these two kind of soils. And for hydraulic properties, most people reported that the coefficient of permeability become larger after freezing sowing cycle. And this is true for both dense and loose soil. And overburden pressure can reduce this tendency. It is also reported that the freezing sowing effects also can erase the pre-consolidation effect. Originally, for over-consolidated soil, we have a pressure here, pre-consolidated pressure here. After several freezing sowing cycles, it will become like this. And usually, for over-consolidated soils, when you conduct a trajectory test, you usually have a peak here. But after several freezing sowing cycles, the strain stress behavior will be like this. So you can erase the peak. Mechanical properties, for example, the resonance modulus, Professor Thomson, his results show that for the first freezing soil cycles, it will drop for 50%. And recently, one author also reported the reduce after freezing sowing cycles. These freezing sowing cycles reduce the regional modulus. But one thing I don't understand in his result, when he apply very large confining pressure, the regional modulus is increasing. This is another person's result. This is the modulus dependency with temperature, with negative temperature. For one freezing sowing cycle, the regional modulus also dramatically drop. But cohesive force also decrease with the number of freezing sowing cycles. This show, but this also showed that the freezing angle is increasing after freezing sowing cycles. And another Professor Qi from China showed that for original loose soil, after freezing sowing cycles, the cohesion will increase, and for dense, you will decrease. Here is also try to figure out the same tendency for the friction angle. So different authors for freezing sowing cycles give different results. So I suggest the test method should be standardized for different authors to can be compared with each other. And very few dynamic properties were studied for the freezing sowing cycles effect. Now I give a very small recent study for the Harbin-Dalian high-speed railway. So in this part, from Harbin to the harbor city Dalian, we are constructing a high-speed railway. This railway is design speed is 350 kilometers an hour. Slab track was used, no ballast. For this kind of high-speed railway, usually very high quality fields should be used. But locally, in some cases, we don't have so much good materials. So local soil was used in cases. Clay was used. So clay used to, but with modification, using the lime and the cement. For those who don't know the slab track, this is the slab track. It's actually a plate on the soil. So for this kind of structure, is required very high quality of subgrade, the soil part. The low bore deformation is 15 millimeters within 20 meters. So for this kind of soil, we conducted dynamic triaxial test. This is a measured soil, measured stress on the subgrade. And the similar loading cycle will apply to the soil we used. There are two kinds of, if the deformation is like this, is good, and if it develops very fast, it's bad. So between them, there will be a critical meaning. We call it critical dynamic stress. So for this original soil, we use clean. We conduct many triaxial tests, apply the pressure. We found that the critical threshold meaning is 230 kilopascal. And then this kind of clay, we add some lime or cement. When adding the lime cement is increased, this is the blend ratio. This is the blend ratio. When blend the lime and the cement, the critical state, critical meaning is increasing. But after several freezing sowing cycles, this will decrease. This is for cement. This line is actually this line. So you can see after several freezing thawing cycles, it decreases this meaning. This is the freezing thawing cycles. And this line is actually this line. So after freezing thawing cycles, it decreases. It's for different blending ratio. So we also, after this test, give equation to predict how much reduce the dynamic strength. And now a few words about Qinghai Tibet Railway. Tibet is used to be the only province they don't have railway in the last century. In this century, the Chinese government decided to build a railway from Gormu to Lhasa. This part is also belong to the Qinghai Tibet Railway. This was constructed in 1980s. In 1982, it sent to exploration. This part. Most total length of the Qinghai Tibet Railway is 1,142 kilometers from here to here. But most of them above the 4,000 meters high. And half of them from here to here, this part is located in the permafrost zone. 1 meter or 2 meters below the surface of the soil is in permanent frozen state. Usually we have this kind of problems. So in Qinghai Tibet, you can find a very gentle slope, but can collapse in winter. Very gentle, 7, 8, 9 degrees inclination. And you can have a frost heave. This picture shows the railways in Russia 100 years ago. At that time, people don't quite understand the frozen soil problems. So this picture we took in very recently. It's a new railway line in Russia after 3 years. This is a new line, actually. So this is because degradation of the permafrost. Usually, we have several factors influencing the stability of subgrade on permafrost. This line usually we call the permafrost table. Beneath the temperature is minus. The first for Qinghai, Tibet, the most important is the solar radiation. We have very high solar radiation in that area. So that part of thermal caused by the solar radiation is very, very large. The second is the summer precipitation, the rain. The rain will take many summers. That will influence the stability of the soil. And the infiltration of water from this side to that side, and increase the thickness of snow. The snow in the winter, on the first winter, is bad because it's like a quilt covered the subgrade. So in Qinghai Tibet, the main principle is to protect the permafrost, because in frozen state, keep them in frozen state, the strength will be higher. We use several measures: crushed rock, thermal pipe, and ventilation duct, dry bridge to protect the permafrost. Back in 1970s, the scientists in China had already begun their studies on the crushed rock. They found that beneath the rock, the temperature is for 2 degrees lower than the other side. And in 1990s, Dr. Goring from Alaska University also conducted investigation on this kind of subgrade. They called it air convective embankment, ACE. Both his numerical simulation and the experimental test showed a high good effect to protect the ice-rich permafrost. The main idea is to using the air circulation or convection to take the heat off. So in China, in the Qinghai Tibet, many places use this kind of. At that time, people don't quite sure what the diameter should be used. So two kind of 5 8 or 40, 50, these two kind of tests were conducted. And many combination of this. People are very interested. People use different steps on both sides to adjust the differential settlement, because suppose this side is south, there will be more settlement. This side is north, will be less settlement. So to put more crushed rock, hope to adjust this differential settlement. And the observation also showed lower temperature beneath these kind of structures. Another very interesting measures is thermal pipe or thermal siphon. I don't know how to use the correct name. This kind of device usually have two parts. This part is outside. The other end is in the soil. You have working material here. When there is a difference in temperature, in winter, when the air temperature is lower than the soil temperature, this kind of material will evaporize to that part and release heat, and then again become liquid, return here. So this kind of device work like pumping the heat from the soil, only in winter. So we are installing this kind of devices on the subgrade to hoping to make the permafrost table rise. This is the Qinghai Tibet Railway, and this is the railway constructed in 1970s in North China. Recently, we put several parties of thermal siphons. And these two pictures I took last September in Russia. People are using these kind of devices to stabilize their home. You see, this is a permafrost zone. When something happens, they usually have put in these kind of devices to make the temperature cooler.
These are cold water or some kind of liquid circulating in the pipes?
Yeah, yeah.
As opposed to the other pipe is just getting the heat out.
Yeah. You have many these kind of devices. Alaska pipe, oil pipe is sitting on this kind of devices. Another measure is duct, air ventilation ducts using the cold air, hoping to cold air come here, and the hot air go from this side. In this way, it takes the heat off. And this kind of shuttle was installed. This shuttle is temperature memorized. When the air temperature is warm, it closed. So it's open in the morning, in the night, and in the noon time, it's closed. This is the bridge is built not for the water to pass, but to no water. This is so we call dry bridge to protect the permafrost. And another measure is shading. So this is a hint from the nature. In nature, you can find the permafrost in the mountains. The south side, north side, you have more permafrost, and the south side, you have less permafrost. So on this idea, we suppose if we cover the permafrost subgrade using some structures, it will be better. Yeah, sure. Many observation data show that it can be for several, at least 3 degrees lower than the outside. But this kind of structure was not used in Qinghai Tibet Railway because of the difficulties in maintenance and high spins. This a result we conducted computation when you have a shading and no shading. It's quite different, the temperature state. We also conducted research on the transition part from the bridge to from subgrade to bridge. We are using the same kind of crushed rock to using the ventilation to cooling the base. And in this part, we're using the traditional changing depths of the crushed rock to make the transition smoothly. This is gel grade I used. And the environmental also was very well protected in this Qinghai Tibet Railway, because in that part the ecosystem is very weak. There are many weak, no trees. Vegetation is very difficult to recover. If in this year you uncover a vegetation, next year, after 3 years, you can also find that part exists. So it's very difficult to recover the vegetation. Many corridors was designed to let wild animals, protected animals, to go through. So the subgrade, we are using very gentle inclinations for them to go through, and above the tunnel, beneath the bridge. So to summarize, we need more sophisticated differential frost have, more sophisticated model to predict the differential soil settlement. And we need to standardize the test method for freezing thawing cycle problems. And we need to conduct long-term stability for the permafrost subgrade. Thank you.
Questions for Professor Liu?
One quick question that I had in mind. You showed those large rocks and different size rocks as a crush rock as a means to maybe control the temperature. Is that right? Those embankment revetments and things you were showing. Convection, I think you mentioned.
Yeah, we are using this.
Can you elaborate a little more about how actually this crush rock, the porous structure, is keeping everything cool? What is the main mechanism? I'm trying to better understand.
Yes, we are using this kind of structure, hoping to let cold air to form a convection, cold air convection in this in the pore of the crushed rock. So in this way to cool the soil.
So cold air is inside, like ground is cold, and you're trying to keep that cold.
Yeah, keep that cold.
Escape, and then rocks are helping.
Keep that cold. Yeah, keep that cold. So we have observation beneath this crushed rock. The temperature really is lower than other part.
Yeah, I think the idea is that you're transferring heat. If it's warmer, you're taking it out, and if it's cooler, you're switching the heat transfer the other way. So I guess the idea is you have to have something that allows air to pass through it. You have to have the rock gradation has to be open graded, or this won't happen. Is that correct?
Yes, but this problem is not quite studied because it's constructed very fast. It doesn't leave time for the scientists to study. You mean the optimal
gradation?
Relation. Yes, that's a good question.
Yeah, because if you get too dense, then there's no convection.
Yeah. Yes. In this part, they try this. This is the experimental part. They try to figure out what is better, which one is better.
What size is better? What maximum size and gradation?
But no answer for this question.
So they like the temperatures of the ground in different cases with different sizes of rocks.
They are now regarding this one is better. The larger is better.
That makes sense. But the rocks there aren't there for structural purposes. They're just there. Is it all the way through the embankment? The rocks that go all the way?
Several structures I didn't show. In some places, the total subgrade embankment was constructed using this kind of. Some places only from the both side or one side, or just the berm. Many combinations.
So it sounds like the challenge with high-speed rail in these permafrost regions are more the embankment stability than whether you have slab track.
Very good questions. For for slab track, it requires very stable subgrade. So here, according to Chinese standard, the aluminum deformation for the whole service time, the service time is in China regarding 100 years. During 100 years, you can keep the soil not deform more than 50 millimeters. It's very difficult. The Harbin Dalian railway also have some this kind of problems. The first heave already have people doesn't pay any enough attention to these problems.
So, can you comment on the design to try to? I mean, what are the strategies to reduce the frost heave there? I mean, just put deeper layers of granular
I
materials.
think personally, I don't like this one. the ballast is better because the ballast, when you have ballast, you can in any time when something happens, you can adjust, you can add ballast or doing something. But this one, when something happens, when the settlement, large settlements, the plate will in bad stress condition. It's very difficult to repair in this. So personally, I prefer this the ballast one. But why they are using the slab track? They regard it's very easy to doing the maintenance work.
For the actual rail.
Yeah.
Yeah.
I was going to say that's one of the primary reasons that slab track is not caught on in the U.S. is that the practitioners in the U.S. like to be able to adjust their track and fix it, and that's something that's very difficult with slab track.
Yeah.
One disadvantage of ballast is that at high speeds, we know the ballast flying ballast, causing all the damage and flying around. That's one issue, I guess, at high speed. The other thing is, again, at the higher speeds, you want firmer ground or foundation with much less tolerance. And I think it's not the ballast, but slabs going through the heave cycles is creating the problem. Basically protecting your subgrade and making sure your subgrade doesn't
That's also
deform. Right? Can you define that intermediate layer on top of the subgrade? The HGT, what's that?
this这翻译一下这。
Kind of like a high stress motor.
What?
High stress motor.
How big? How thick is it? They call it asphalt mortar. Is that the?
It's not asphalt. It's kind of like artificially engineered.
这是砂浆
high quality cement.
，C 砂浆。
What's the purpose of it?
So you need to prepare some road bed to let the engineer and adjust the height when you place the top slab track.
Oh, the slab track actually is precast.
Yes.
Precast, precast.
That's why we can build it so fast. Yeah. It's kind of like leveling.
It's like using HMA now on the expressway.
Does the actual slab track system increase it would increase the amount of heat that's flowing down, though, wouldn't it? Thermal conductivity?
这是什么？
他是问那个轨道板会不会把底下的那个温度提高，就是说它的那个热透性会不会提高？
Oh, I don't know about this. I'm not sure. But for people are studying the vibrations for permafrost reason, some researchers are studying the vibration of the track structure, how much increase the temperature of permafrost. They have some results. It's really influence the temperature of permafrost. This is the plan of the Chinese high-speed railway. This is a 1 hour cycle. This is Beijing, 1 hour cycle, 2 hour cycle, 3 hour cycle. So the longest is the 24 hour cycle to Tibet, Lhasa, Lhasa.
All those red lines are finished, right?
Planned.
Planned.
That's the high-speed rail, China's high-speed rail plan, right?
Yeah.
Any other questions from further back? Doesn't anyone want to ask if they use asphalt for a rail bed? Do you use any asphalt as a sub ballast or something?
是不是要问我用没用那个沥青 ？No, I never encountered this kind of.
No HMA track, but HMA track.
Well, they have
No.
a couple areas. I remember reading that in Rose's paper from, I think, JRC 2010, but there is some use of it, but it's not as widespread in other areas. So, really positive.
Well, let's thank Professor Liu for his presentation on this. Thank you.